This lesson is going to be about friction in systems, and the learning target is to be able to describe how friction affects the energy of a system. So friction is a force that resists the motion of two surfaces that are touching. And we know what friction is, if we thought about this force, the reason why we can't slide across a carpet as easy as we can slide across like an ice rink. But if we look really closely at what's going on when two surfaces slide across each other, as I try to zoom in here, we've got one surface and we're moving in this direction, and we've got the other surface moving in this direction. And there's these little microscopic ridges and valleys. And with something with like carpet, you can see these ridges and valleys. You can see the little fuzz balls that come up from your carpet, or you can feel that it's rough, right? But if I feel like a soft tabletop, or a smooth tabletop, I should say, right, I might not necessarily be able to feel all of these little ridges, but they're there. And every surface is different, right? That's why carpet has different amount of friction than like an ice rink would. But as one surface moves across another, these little peaks, valleys, ridges, whatever you want to call them, are going to push against each other, and they're going to resist the movement um, of those two surfaces, and it's going to cause a force, some resistance, to happen as we move it. So, like we said, if we go back to what we learned in forces, as objects move at a constant velocity, as they're not speeding up, slowing down, or anything like that, that means that the net force on them is zero. Well, when we pull this block across the surface, even if we pull at a constant rate, means that the net force is zero, we're still going to see some sort of force showing up on the spring scale. That means that there is a force resisting our motion. Right? If we look at the block, we're pulling in this direction, force applied. We know that it's moving at a constant rate, so there must be some other force opposing that motion in the other direction. That is the same as our applied force, and that is our friction force. And so the friction force is going to oppose motion. It's in the opposite direction, and it's going to depend on the type of surface that we have. And there's a couple different factors that affect it. First, the mass and really the normal force affects the friction, because the more that these two objects push together, the more resistance there's going to be, the more likelihood that we're not going to be able to overcome the resistance from these little peaks and valleys that are going on between our surfaces, right? So if you look at my example here, if there's 50 kilograms on this simulator here, and we're pushing, my friction force is 94 newtons. Now, as I add more weight on top of there, I increase the normal force. Remember, the normal force is the force that's coming straight up out of the surface. So that's the force between um, the box and the floor here. As I increase that normal force, my friction force goes up, right? Because those two surfaces are pressed together harder, and so there's going to be more resistance as I try to push that. And as I increase the mass on top of this, these two surfaces are pushed together even more, and so my friction force goes up. And so the mass of our object increases the amount of frictional force that's acting on that object. So you can think about, like, if I was trying to push, I don't know, a chair across the floor, or if I was trying to push a chair with my brother sitting on it across the floor. Not only does he have more inertia, but there's also more friction between his chair and the floor. And the type of surfaces affect friction. This is something that we realize because we feel this all the time. If you're trying to skate across an ice rink, you're going to slide pretty easily, right? That has a low coefficient of friction, is what we would call it. That surface does not have much friction associated with it. If I'm trying to slide across my carpet, I'm going to get a big rug burn because there's a lot of friction associated with that. Right? If I'm trying to push maybe something like a cinder block across carpet, well, that's going to be pretty tough because both of those surfaces are very rough. If I was trying to ski across my carpet, right, I'd probably be able to do okay with it because we know that these are pretty smooth. There's not a lot of friction associated with those skis, especially if you wax them up. That's why you would do that if you're going to go out skiing, right? So you have less friction, they slide easier. Now, if I paired up these skis with an ice rink, now I'm really going to slide. And so the type of surfaces affect friction. It's not only the surface that is being slid across, is that the object is sitting on top of, but it's both of those objects and how much, essentially like how rough is that surface that that are trying to slide across each other. So we got to think about both surfaces. So the goal for this lesson was to be able to describe how friction affects the energy in a system. And the way that happens is friction turns the kinetic energy in a system into thermal energy. If you think about Like when you're running and jumping and rolling across a like carpet, you get a big rug burn, right? Because your skin gets hot. Or if you're like this guy here, you take your hands, rub them together, you can feel them start to warm up if you're really cold out. That's what's happening there. The kinetic energy from your hands is turning into thermal energy, which heats you up. If you had something like, I don't know, you're trying to sand down a bunch of metal for any of you that have maybe Mr. NC's class where you're working on there. If you've ever touched a hot piece of wood after it's been sanded down, it gets really, really, really warm because there's a lot of kinetic energy going on right here. And as it makes contact with that other surface, what you're doing when you sand down wood is you are rubbing off the outside all of those little hills and valleys and peaks and ridges and whatever you want to call them that we talked about earlier. You're rubbing those off of the wood to make it smoother. And so in order to rub those off, you've got to actually physically break them off. And so a lot of the kinetic energy is turning into thermal energy, which gets really hot. That's essentially heat. And so our kinetic energy is turned into thermal. It's the same thing with like an engine. That's why we put oil into it. If you didn't have any oil in your engine, all these metal parts would be rubbing past each other and you would have a lot of friction between those. So your engine would get really, really hot. And so what the oil does is it lubricates the engine so that as those parts are rubbing past each other, if you felt oil before, it's really slippery, there's a lot less friction in your engine. And so the temperature is able to stay cool. And so the big idea, I guess, behind this is that the more friction you have, the more kinetic energy you're going to turn into thermal energy. Now the problem with that is that kinetic energy is a type of mechanical energy, and so it's like usable, and so it's something that can do something. But thermal energy, all it can do is heat things up. We can't really use it to move an object. Um, well, I guess we'd have to do it in a certain way. You could probably find a system that does that, but it's not necessarily that mechanical energy that we would think about, um, like a potential or kinetic energy. And so if you're thinking about like our skater here, like we've talked about before, when my skater's up at the top, he's got a lot of potential energy. And as he rolls down this hill, right, we know that his kinetic energy is going to start to go up. Well, the thing is if we have friction, that means that as his kinetic energy goes up, his thermal energy is also going to go up. There's going to be heat produced between the rubbing between his skateboard and that ramp. And so some of that kinetic energy, that usable energy that means he's moving, isn't going to be usable anymore. It's going to be thermal energy, as you can see right here. As he gets past that little valley in this skate ramp, whoops. As he gets past this little valley, as he's speeding up, this is with friction on now, his thermal energy rose. Because as he was moving, that kinetic energy turned into thermal energy. But notice what happened here. The total energy of the system did not change. The total energy of the system is the exact same. The only difference is now it's not just between kinetic and potential energy, we've just got this thermal energy. And so as he moves back and forth, this is why he would slow down over time, is because as he moves back and forth on this ramp, more and more of his kinetic and potential energy is going to be transformed into thermal energy. And that's not coming back. That gets released to the universe. It would go off, it'd either heat up his skateboard wheels, it'd heat up the ramp, it'd heat up the air around it, but it's not going to be able to be used to move him up and down um, that ramp. And so even though we have energy that's being lost to thermal energy, the total energy does not change. That energy is not disappearing. The reason why he's slowing down isn't because the energy is just vanishing. It's because it's being transformed into kinetic energy, or into thermal energy, I should say. And so the big idea of this is that friction takes kinetic energy and turns it into thermal energy. It's going to heat things up, but that energy is not going to be able to be used to move an object anymore. So I hope that helps learning how friction affects the energy of a system.